So with all this talk about barycenters and the moon, being over here, minding its own business, if you happen to be a sucker stuck on the surface of Earth, how is all of this moon's gravity and all this flip-flopping around the barycenter affecting your daily life? Well, we're going to test two extremes. We're going to test somebody who's standing on the back of the planet here, minding their own business, and we'll test for somebody who's standing here, not to scale. So on the far side of the moon, there are three forces working on you there. There's the force of gravity from the Earth, and we would calculate that by doing your mass multiplied by 9.8, because you are standing on the surface of the Earth. Then there'll be a force of gravity on you from the moon, and we could calculate that. That would be G, M from the moon, M from you, and then how far away you are squared. So G is 6.67. I can hear you screaming at 3 o'clock in the morning, this number, in your dreams. 7.35 times 10 to the 22 is the moon's mass. And if you are standing here, you are an Earth-Moon separation plus an Earth's radius away from the moon. So 3.84 times 10 to the 8 plus 6.38 times 10 to the 6 squared. So let's see what that is. Okay. 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 equals, divided by 3.84 times 10 to the 8 plus 6.38 times 10 to the 6 squared gives me, oh goodness, 0.0000322 newtons multiplied by your mass. So that number is 32.2 micronewtons per kilogram. Okay, now considering that the gravitation here is 9.8 times your mass, which equates to 9.8 newtons per kilogram, this is essentially nothing. It's like a 1/1,000,000th of the effect that you're getting from the Earth's surface. So that's not a lot. The other force that we're going to be experiencing is this winging around the outside as a result of the Earth being rotated around its barycenter due to the moon. So I'm going to have to get a centripetal force there. So that would be mv squared over r. Okay, we don't really have the speed, so I'm going to re-coordinate this for period and radius. So if I keep the m and the r, and I replace the v with 2 pi r over t, and then square it, I end up with 4 pi squared, an r squared on top divided by an r, leaves me with an r m over period squared. So the centripetal force then would be 4 pi squared, the radius from your center of rotation. So that would be a radius of the Earth plus a radius of the barycenter. So that's 6.38 times 10 to the 6 plus 4 times 10 to the 4.66 times 10 to the 6. then this orbital period for the moon is 27.3 days. I'm gonna have to look that up. Okay, well, the Google is saying just 27, so let's just go with 27 days. But I need this in seconds. So 27 days times 24 hours times 60 minutes times 60 seconds. And I'm going to have to square that. Okay, so 27 times 24 times 60 times 60. It's going to be 2332800. I'm going to square that. Something times 10 to the 12, put it in the denominator, times 4 times pi squared gives me times 6.38 times 10 to the 6 plus 4.66 times 10 to the 6 and bracket gives me 0.00008 009. M, because I don't have an M in there yet. Okay, so that equates to 80.09 micronewtons per kilogram. Now that doesn't feel like very much. Okay, good. So if I were to take these numbers on this side, I'm just going to erase this little line here. The force net on the far side ends up being 9.8 times your mass going this way, so positive because it's going that way. And then I have a force of gravity from the moon, so that's plus 0.000322 m. And then I have a centripetal force throwing me out, so that will be subtract 0.123480009 times my mass. Okay, so I'm going to erase these so I have some space. So if I were to add this and subtract that, I would have 9.8 plus 0.1234322 subtract negative 0.00080009. Oop, too many negatives. Gives me 9.7999521 m. So that's your net force. So your acceleration would be just this number divided by m, so you end up with 9.7999521. Okay, lovely. Get rid of these. Now I'm going to repeat all those calculations for this cat on the close side. So a force of gravity from Earth will be 9.8 times m. The force of gravity from the moon will be 6.67 times 10 to the minus 11 times the moon's gravity, or moon's mass, sorry. And when I'm standing here, I am a full moon length less a radius of the Earth. That's 3.84 times 10 to the 8. Subtract a radius, which gives me 3.84 times 10 to the 8. Subtract 6.38 times 10 to the 6. Park that denominator times 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22. Oh, I forgot to square the denominator. Don't forget your squares. 8.84 times 10 to the 8 subtract 6.38 times 10 to the 6 equals, square that, put that in the denominator, times 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22. There we go. 0.0000344 m, which equates to 34 micronewtons per kilogram. Alright, now that is slightly more than we had on the board before, but not very much. Your centripetal will be mass v squared over r, which ends up being 4 pi squared mass r over t squared, which will end up being 4 pi squared. The radius of your rotation now is the difference between an Earth radius and a barycenter, right? Because you're that far from the point of rotation. So that will be an Earth's radius subtract the distance to the barycenter, m, over 27 days times 24 hours times 60 minutes times 60 seconds. .38 times 10 to the 6, subtract 4.66 times 10 to the 6, times 4 times pi squared, divided by 27, divided by 24, divided by 60, divided by 60. Did it again. Squared. Divided by 27, divided by 24, divided by 60, divided by 60. Gives me 0.0000125. So with all these numbers gathered up, I'm going to do the net force on the close side to the moon. So that's this one here. So F net on the close side. That's close side to the moon. I would have 9.8 m. On this side, that's gravity from Earth, so it's pointing to the left. So I need a negative in front of that. And then I have force of gravity from the moon. 2, 3, 4 zeros and 394. Okay. And that's pointing to the moon over here, so that's positive. Then I have this centripetal force, 0.000125. And that centripetal force is pointing away from the center of rotation. So that's in this direction, that's positive. All right, so I can add that up to get my net force. These have m's on them. So negative 9.8 plus 0.000394 plus 0.000, oh, there should be an extra 0 in there. 0.00125 gives me negative 9.7995935. And of course, with the m on there, if I divide m's on both sides, I get this as my net acceleration. So if I were to look at the net acceleration on the far side of the planet from the moon and the net acceleration on the close side of the planet, there is not a lot of difference. I don't get a change in the digits until after the 5. So 1, 2, 3, 4, 5, 6. That's in the 10 to the 6th position. That's micronewtons. The difference between 2 and 9 then is 7 micronewtons. I'm going to erase this and then put that up the top of the board. That is not very much. So when you're on one side of the planet or the other side of the planet, the presence of the moon doesn't change things much. There's only a variation that big. But there is something I'd like you to spot here. So I'm going to just modify this a little bit. I'm going to take out the Earth's gravity for a second. We're going to look at just these two terms. So if I just do these ones, 0.1234322 minus 0.1234809 gives me negative 48.7 micronewtons per kilogram. That's negative 4.87 times 10 to the negative 5. And on this side, 0.1234394 plus 0.1234125 gives me 51.9 micronewtons. That's 5.19 times 10 to the minus 5. So I end up with accelerations that are just these are per kilogram, I guess. So I get an acceleration of negative 4.87 times 10 to the negative 5 meters per second squared and 5.19 times 10 to the negative 5 meters per second squared, which is not a lot. Something else I'd like you to notice. This term and this term always pointed to the right. So that doesn't change, right? It gets a little lower as you go over here because you're getting further from the moon. But this term does change. This one swings from negative to positive. So at some point, this term and this term are going to end up, like if you look, this one's negative 0.000809. That's more than this, but it's negative. As this term is increasing to reach this value as I go around the planet, at some point it's going to have to pass through a value where it ends up equaling this, but negative, right? It'll have to go through negative 0.0000322 before it can get to this value. So there's a place somewhere on the planet, somewhere up here and somewhere down here. Let me mark them for you. Somewhere here-ish and here-ish, where this centripetal term negates the gravity for the moon. And if that happens, then the acceleration you're experiencing is 9.8 meters per second squared. You're dealing with only Earth's gravity. So what I've got set up here for you is that at a point somewhere around there and a point somewhere around there, you are feeling Earth's uninfluenced gravity. But on the side closest to the moon, you have an imbalance. You have it being slightly less force on this side, so that things have an acceleration 4.87 times 10 to the negative 5 less than what they are under Earth's normal gravity. On this side, you also have the same thing. You have 5.19 times 10 to the 5 less than Earth's normal acceleration. So you're being pulled harder here than you are there. And so any material that is on this side and this side of the planet will start to be pushed outwards because this force is stronger. So it's like squeezing a plastic Easter egg, right? If you squeeze the top, then the center has to bulge out. So because I have an acceleration, right, on my far side, I have an acceleration that's pointing that way. So I'm going to get a bulge that grows like that. And on the inside, the close side, I have an acceleration pointing that way. So I'm going to get a bulge on that side. Now this is not to scale. But these teeny tiny micronewton differences in the gravity and centripetal force terms, if you add them all together, leads to a bulging on both sides of the planet. Now, for Earth, which happens to be covered in fluids, right? Gases, so your atmosphere, and liquids, like the oceans, those materials flow quite easily. So if you have liquids that are being pulled harder in this direction and less hard in that direction, then they will bulge out. So you end up with an amassing of liquid and gas on this side, and another one on this side. So this one is the one we're used to, right? The moon sits out here and it attracts the water towards it. And so if we find that on the close side, indeed, that's gravity pulling you up. And it is assisted by the fact that the barycenter is flipping you around. But the one that you're not expecting is the one on this side, right? If the moon is over here, water shouldn't be repelled away from the moon. That doesn't make sense. But the fact that the moon is big enough to cause the barycenter of the system to be off-center on the Earth causes this term here, this centripetal force term, to overpower the additional gravity from the moon so that you end up with a net acceleration away from the moon. And so those two lumps of water and gas sort of form as a result of the moon, and the planet, as it turns through its day, rolls into the bulge and then rolls back out of it. So if you were to look at this system, we're used to thinking of you stand on the ground and the moon drags the water up over the land to make high tide. That's not exactly how it works. The bulge is there, and you rotate into the bulge for high tide and then rotate out of it for low tide, and then it happens again 12 hours later. Tides are not 24-hour cycles, they're 12-hour cycles. So there must be a bulge over on that side, and it's because of the centripetal force. So that's kind of neat. If you're thinking that these numbers are kind of small, 10 to the minus 5, right, like they're micronewton differences, that is not a lot of force, but those micronewton forces in the moon-Earth system are able to raise the tides in the Bay of Fundy several meters. So you get quite an effect, like quite a human scale effect from these micronewton forces. I'm going to ask you to do this whole process the other way. So I'm going to ask you what happens to the moon as the result of the Earth. So like if the moon was covered in water, what would its tides look like? And you're going to get numbers that are much bigger than this. And so you're going to be able to think about what would happen to like a stony object if you were able to raise tides, like if the forces were strong enough to actually lift the rock. And if you do a little reading about it, that's what's happened to the moon. The tides are so strong on there that it has lifted the crust from the moon so that it's kind of oblong. And because it's become oblong, one face of it is always stuck pointing at the Earth. So the moon may have rotated on its own axis at one point, but because it got to be a little egg shape, eventually it slowed down and it tried to turn, couldn't finish, swung back, swung back, swung back, swung back. So that face, the man of the moon as it were, is always pointing towards us as it makes its pathway around. So you're going to be able to do this calculation and see the kind of micronewton forces that are necessary to actually tidally lock, that's the phrase, a moon so that one face is always pointing at the planet it's orbiting.